Okay, so let's start with the discussion session. I'm also taking the cue from Tracy to sit down and talk. So.
This whole thing.
Yeah, so welcome everyone. So today is the open discussion session. So I am happy to talk about whatever you would like to talk about related to indirect detection. You know, if people are interested, we can start by going into a bit more depth on the anomaly, or like answering your questions about the anomaly, since everyone, held their questions last night. So if people have questions about that, we can talk about that. But we can also, if you have questions about indirect detection more generally, anything we talked about or topics that we didn't cover, I'm happy to, discuss that as well. So I guess, does anyone have a question or thing they want to hear about to begin with? Yeah.
Yeah, so for the positron access, you were talking about how it is difficult to come up with a dark matter model that is a thermorelic and freezes out in the way that we like it to. I'm wondering, is there a possible freeze in then annihilation to positron scenario?
Wait.
So yes,
You guys. Sorry, I'm just trying to. Okay, so this is like, wait, sorry. Just need to find the correct. So yeah, so right, so this was going back to this positron access, yeah. So I was saying, so okay, the problem. So if we had a freeze-in scenario, that typically corresponds to much tinier couplings than the freeze-out scenarios. So I would think that if you have an annihilation, like, okay, so let me, I'm thinking out loud a little bit here. So if you have an annihilation cross-section large enough to give this signal, then unless the annihilation was extremely suppressed in the late universe, it would also be large enough to keep the dark matter in thermal equilibrium with the standard model. Like the fact that this cross-section is way above the usual thermal freeze-out cross-section tells you that unless it was like the cross-section was badly suppressed for some reason in the early universe, the reverse process should have been enough to bring the dark matter into full thermal equilibrium with the standard model, and actually to keep it in thermal equilibrium for longer than you want. Like that's the problem that if you have, when we say highly thermal cross-section, that means that for a cross-section this high, you would typically deplete the dark matter too much in the early universe, you would keep it in equilibrium for longer. So maybe you could do something like that, but I think you would need to have some mechanism that such that the annihilation cross-section, such that there was basically no coupling with the standard model at early times, and then at some later time that coupling turned on and became large, which you might be able to engineer, but it seems like it would require some non-trivial model building. And yeah, this is a discussion, so other people should feel free to speak up, give their own thoughts on this issue, say, no, it's totally easy to do that, Tracy. It's not as hard as you think. So, people should feel free to chime in. But yeah, that's a great question to start with. So yeah, I mean, in terms of right. So I mean, what you could imagine having is some kind of non-thermal production mechanism followed by a decay with a long lifetime. Because decays, as we talked about, become more important as the age of the universe gets larger. So like you can have, if you have a long lifetime decay, it would not have been enough to, it wouldn't have been enough to bring the dark matter into full thermal equilibrium with the standard model early on. So maybe you could do something with that. But yeah, for annihilation, naturally it's much larger at late time. So you need like some factors to compensate for that if you want it to be tiny at early times. Sorry, so annihilation is actually larger at early times. I'm not sure if that's what it's okay.
So in this anti-helium business, so you said that the background is expected to be pretty much zero.
Yeah.
I don't know how zero. That seems.
I mean, not zero, but so I would need to double check this Paul et al. Paper about yes, there should be some anti-helium background, but so this Paul et al. Paper, and I would have to double check whether this was like just the background or just the signal or the background plus the signal. But these blue and red line, those blue and red lines on that plot were their forecasts for the number of like anti-helium events you would expect to see. And that gray region up above is the expected sensitivity of AMSO2. So like not zero, but you know, 1 to 2 orders of magnitude below the sensitivity of the telescope.
And sorry, what's the difference between the red and the blue here?
One is anti-helium-4 and one is anti-helium-3. That's the other funny thing about what AMS is claiming to see. If you think about just production of like anti-helium through lighter particles collide and occasionally some of them coalesce, then the probability to get 4 nuclei coalescing is significantly smaller than the probability to get 3 nuclei coalescing. Like they're both rare events, but having to have the extra nuclei in there makes it significantly harder, which is why the red line is like 2 orders of magnitude below the blue line. But what AMSO2 claims to see is 2 anti-helium-4 nuclei and 6 anti-helium-3 nuclei, which are not very different numbers. So that's the other thing. I mean, like if you look, you know, in our universe, it's mostly anti-helium-4. It's mostly helium-4, I think, not helium-3. So like this isn't strange. Like if the perspective was, you know, what if there was a region where there was as much antimatter as ordinary matter and it had gone through nucleosynthesis like ordinary matter? But which was the main focus of this Poulin et al. Paper, was to consider the case of, you know, what if there are like regions of what if there are antimatter regions where the antimatter is, you know, where there's very little matter and almost all antimatter. But the question of how you form those regions in the early universe without having them mix with ordinary matter and stay like as pure as they would need to be throughout the history of the universe, as I understood it, seemed to be the challenge for that interpretation. Like if you just say, okay, what if we had an anti-star in the galaxy? How much anti-helium would that make? Then, you know, then you can explain what's going on. But then the question is it really plausible to have an anti-star, a star made solely of antimatter in our galaxy? Today, it might be virtually collisionless, but at earlier times in the universe, the density has been higher. You would have thought that it would have interacted with ordinary matter, and it would be hard to get a star just made 100% of antimatter. So again, if other people in the audience want to speak up and say, you know, and comment on that, then, you know, they should feel free to. But that was my understanding of this Poulin et al. Paper. Like it is technically possible to do this with like antimatter regions nearby, but my recollection is they need to be inside our galaxy, so they need to be relatively close to get flux high enough, and it's not obvious how you would do this from cosmology, but the problem is getting them there. Like if you can say, you know, aliens somewhere in our galaxy have built a star made entirely of antimatter, then you know, then it is possible to explain this kind of signal.
But in Voyager, I don't know what's on Voyager, but they don't have the capacity to check this.
Voyager, I don't think can tell the difference between matter and antimatter. I don't think they have a magnet. Like AMSO2's magnet is a pretty serious magnet and was like a good chunk of the difficulty of the experiment. And most other experiments looking for cosmic rays do not have a magnet for the charge discrimination. So I think it would be hard.
Are neutron stars and quasars the background for helium?
So usually in pulsars, we think that you get efficient pair production of positrons and electrons, but probably I don't think we expect there to be enough energy to do efficient pair production. Well, yeah, what do I need? Yeah, I have never seen a suggestion that we expect significant hadronic emission from pulsars. Like, I just don't think we expect the pair production rate into protons and antiprotons, or much less heavier nuclei and antinuclei, to be significant. I guess if I think about that said, I mean, they are making like multi-TeV positrons. And so, you know, you would look at that and say, okay, well, there's clearly enough center of mass energy in like available to possibly make the heavier antinuclei. So I guess it must just be that the branching ratios are expected to be very small, but I don't know how tiny very tiny is. So yeah, I mean, maybe that's something to look into. But the conventional wisdom is that pulsars make gammas, electrons, and positrons, but not really anything heavier. But yeah, I don't know the full roots of that conventional wisdom.
I have a question. On this, when you're talking about the 3.5 kV line.
Yeah.
We were talking about that there's some kind of strategy where we can look for Doppler broadening. I think.
Doppler shifting and Doppler broadening. Yeah.
So why would that help nail down this line?
Yeah, great. So, okay. So at the moment, all the observations of the 3.5 kV line are with instruments that have like okay, but not great energy resolution. So when you see a line shape, what you see is the energy resolution of the instrument. You're not seeing the intrinsic width. You're almost certainly not seeing the intrinsic width of the line. And when they look at the data and they perform a fit to the data, what they're doing is fitting a profile, which is the energy resolution of the instrument. So any line that is narrower than the energy resolution of the instrument, or any like collection of like 3 lines that are packed together more closely than the energy resolution of the instrument, will basically just all look the same. They'll have the line shape of the energy resolution of the instrument. So that's what you're comparing to the data points. Okay. And that seems to describe the profile of the signal really well, which is like good evidence for it being not just an instrumental effect, but some kind of, I do think they've seen some kind of astrophysical signal because for multiple reasons, but that the signals from different clusters appear to be at the same energy after you redshift them. And also this 3.5 kV line at this point has been seen in like 3 different X-ray experiments. So it's probably not an instrumental effect. It's probably like, it's likely something out there in space, unless it's a whole bunch of coincident statistical fluctuations. But it's probably something out in space. There was a question up there.
I'll shout. So this 3.
No, please.
I won't shout. Hang on.
Yeah, I guess while that goes past. So if you have a better energy resolution experiment, you can try to look for the underlying width of the line. And that has a few different contributions, but let me take this question
Sorry.
first.
Yeah, so you mentioned briefly that there could be some kind of astrophysical explanation for this.
Yeah.
Is there kind of a leading theory as to what this could be? Because I understand clusters are very busy systems when it comes to X-rays. So
Yeah.
could this be some kind of new astrophysics?
Yeah, so good. That's a good question. Let me say the thing about the shift first, and then I'll talk about the possible astrophysical observations a little bit. So, right, so then you asked, okay, what are the contributors to the actual like physical width of this line if we have energy resolution good enough as to see it? Like at the moment it's a moot point because the energy resolution is pretty broad. So one contributor can be like, the width of the line is governed by the intrinsic particle physics width of the line is governed by the lifetime of the decay. That's why we sometimes call it a decay width. Okay, but that lifetime to get this signal right is like 10 to the 29 or 10 to the 30 seconds. So that width is really small. So like from that perspective, this line is a Doppler function in terms of intrinsic particle physics width. But there's another source of broadening, which is that the sterile neutrino. So suppose this is a sterile neutrino decaying somewhere out in the dark matter halo. Okay, we're moving relative to the dark matter halo. So those sterile neutrinos are not at rest in the frame of the Earth. So there are 2 sources of them not being at rest. One is like the bulk motion of the Earth. Or effectively the bulk motion of the halo relative to us. That, if we're going around the galaxy like in this direction, then particles over there are coming towards us, and particles over there are going away from us. Okay, so that like boost from our rest frame to the so in the sterile neutrino rest frame, the photon that comes out will have half the energy of the sterile neutrino. Okay, like that's just energy, assuming that treating the other particle that gets emitted as massless. So say in that frame, the photon has 3.5 keV of energy, but in our frame there's a boost. That boost is a Doppler shift. So the photons coming towards us will be slightly blue shifted, and the photons going away from us will be slightly red shifted. So that's one effect. But in addition to that, the dark matter particles are not just completely stationary within the dark matter halo. They have some velocity. They have some we guess approximately isotropic velocity dispersion relative to the dark matter halo. So even the particle that's over there, like from the motion of the halo, they're all coming towards us with some velocity, but then each of them has some individual intrinsic velocity, which could be in any direction. So there's an overall shift, but then there's also a broadening, and both of those are from Doppler shifting, and the parametric size of these 2 effects is the same. So ideally what you would expect to see, so if you could really nail down the energy resolution, what you expect to see from a dark matter signal is a line that has a characteristic width set by the velocity of dark matter particles in the halo, which is not the same as the velocity of the gas in the halo necessarily. And you also expect to see a shift when you look at different parts of the halo, which corresponds to something which is, something where the overall distribution is at rest relative to the dark matter halo. And like, we know how fast we think we're moving relative to that halo. So that would be diagnostic. Like, if you see that, it tells you that it looks like something associated with the dark matter halo, not with the gas of the galaxy, because the gas in the galaxy is co-rotating with the disk. So like, it's co-rotating with us. Okay, yeah. There's a paper which the last exercise in the notes is basically working out what energy resolution you need to see this, but the answer you get should be an energy, like, so parametrically, the velocities of dark matter particles in the halo is 10 to the minus 3 times c. So that means that the relative Doppler shift is of order 10 to the minus 3. So on a 3.5 keV line, that means you need an energy resolution of about 3 eV to see it. That's hard, but we have actually built X-ray telescopes that have energy resolution of 3 eV. We built one such X-ray spectrometer and put it on an instrument that was called Hitomi, or Aug6, and it was launched a few years ago, and it sent back beautiful, beautiful data for about a week. And then there was a programming error and it broke apart. And it was extremely sad. In the like 2 weeks between when it launched successfully and when it broke up, I went to Goddard, and one of the people working there had like spent years building Hitomi and launching it. And I was like, oh, you had a successful launch, you must be so happy. And he's like, yeah, it's awesome. We're starting to get data. It's so great. And they got initial data from the Perseus cluster, and it was beautiful. It was pristine. And then there was this breakdown. And the breakdown was basically because there were two fails. There was a baseline code to stop what happening, and there was a failsafe, but they didn't sufficiently test the failsafe because it was just a failsafe, and surely the main one wasn't going to fail. And so then the main thing failed, and then the failsafe also failed. So that was very unfortunate. So always check your code, even if you think it's just the backup. So there are future X-ray experiments that should have comparable energy resolution and should ideally be able to do this for us. I think the shortest term one, the possibly shortest term one like that, is a sounding rocket experiment called Micro-X. So the way that this works is, you don't need to put it in space. You put your spectrometer on a rocket and it goes up and it comes down and it's up there for like 5 minutes, but that 5 minutes is still enough to do decent observations of the galactic halo, and you can make the energy resolution really good. And they have done a test flight with this, like to check that the instruments work and that the rocket works, and that was before the pandemic. And then their dark matter flight was, I think, initially scheduled for 2021, but it got delayed along with everything else. And I don't know what the current schedule is. But I mean, the nice thing about this is, like, if you send it up and I mean, last I looked, their estimated sensitivity to dark matter with a single flight was like, you would only expect to see like a 2 or 3 sigma signal. But if you see a 3 sigma signal, you just do another flight. Like, this is not a case where your 2 or 3 sigma comes from 10 years of observation. It comes from one flight. So yeah, so that would be cool. But then there are other future experiments. I don't remember, like EXTP and XRISM and some other future experiments. I don't remember. I can point you to the references, but I don't remember offhand which one of these is the energy resolution is amazing experiment. If anyone in here does know offhand, then please speak up. But yeah, within the next decade, we expect to have like actual, long-term, I think, space-based telescopes that can get energy resolution small. So then the question might be, okay, but like, what are we trying to distinguish it from? So your question, which is sort of, what are the astro backgrounds? So this is the sentence that I wrote down here at the bottom. So when this signal first came out, the explanation that a lot of attention went to was there are lines from like potassium and chlorine and argon in roughly this part of the spectrum. And so you can ask the question of, well, are we just misidentifying one of those lines? There's the paper series on this. The first one was called Dark Matter Searches Going Bananas, because bananas are rich in potassium, coming back to the radioactive banana thing from Jodie's talks. And there was a spirited exchange of views back and forth on the archive in response to that paper, which you can go back and read if you're interested. But basically the issue here is the strength of these lines depends sensitively on the temperature and density of the gas. And so the question was, do we sufficiently well understand the temperature and density of the gas? And the people arguing that these lines couldn't be important says, yes, we know the temperature and density of the gas because we can observe all the other lines in the forest. And from that, infer the temperature and density of the gas, figure out how large these lines should be in this region, and say that they're significantly smaller than the excess that we're seeing. So it seems, as far as I know, the leading explanation at this point is not one of these. It is a process that's called a charge exchange reaction, where you get heavily excited, where you get like heavily excited versions of some metal. What do I want to say? You get a situation where you have like heavily ionized versions of some element, and then they can swap electrons to and fro with the surrounding gas. I think like sulfur is one of the elements that's the culprit here. So, and this can make a like structure of several lions around 3.5 kV. And there was an experimental test of this in this paper by Shah et al. In 2016. If you look up like Shah 2016 3.5 kV line, I think you'll find the paper. But like they did an observation in the lab of these charge exchange reactions and showed that you could get a structure around this energy. And this, and again, so this is another place where energy resolution might help you if what we're looking at is actually like several closely spaced lines rather than, you know, just one line. Then better energy resolution could potentially allow us to see that. With the current energy resolution that we have, which I think is closer to, you know, I think is closer to 10% than this 0.1% level, then you wouldn't be able to tell the difference between these lines. So yeah, so one of these 3.5 kV line papers looked out in the Chandra deep fields, which are the sort of outskirts of the galaxy, and they claimed to see the 3.5 kV line out there, and so they said in that paper that it may be pushed a little bit against this charge exchange reaction interpretation, because you would hope that the sort of outer regions of the galaxy are like pretty quiet, pretty quiescent. You don't have a lot of like highly energetic, highly ionized atoms out there. But I mean, it was not a very strong statement in that paper. They were not like, we can definitely kill this. And the other part of what's going on, of what might make you a little suspicious, is that when you look at this, when you look at the different observations that are feeding into the 3.5 kV line, you might note that up here there's you know, this number one signal is quite a bit higher than all the other observations. So that was the Perseus cluster. And in particular, if you look at the very core of the Perseus cluster, the extracted 3.5 kV line amplitude is quite a lot larger than it is in any of the other reconstructions. And so that like week or two of data that we had from Hitomi did look at the core of the Perseus cluster, and they actually wrote a paper saying we can exclude the 3.5 kV line, which sounded very exciting, but it turned out that all they were excluding was the very high version, like the very high extraction of the 3.5 kV line from the core of the Perseus cluster, which was like a factor of 20 higher than the rate that you needed in any other location. So, you know, if you believed it was sterile neutrino decay, you already believed that that detection was spurious, because there was no way you should have gotten that big a signal. And he told me, you know, looked for that and didn't see it. But, you know, if Perseus, when I talked to people who were pretty enthusiastic about the sterile neutrino interpretation, about what they thought was happening in Perseus, they said, well, in the core of a big cluster like that, these charge exchange reactions might be important. So they were thinking that in Perseus, you might be getting a contribution from charge exchange. And then also the sterile neutrino contribution that was, you know, that was showing up in other locations that were quieter and had less background. Yeah, I mean, I have to say that makes me a little bit suspicious. Like if I can say the charge exchange reactions are capable of explaining this huge signal in Perseus, then to me, like Occam's razor is maybe they are also explaining the smaller signals that we see in other systems. But, you know, I mean, this is hopefully something that will be tested by data with better energy resolution in the next few years. So like, I mean, so yeah, I mean, the stronger argument against the simple sterile neutrino decay explanation for me is this fact that, that there have been other observations of the sky that appear to, what you would expect there to be a decay signal, and you don't really seem to see anything. Although you can see that, like in this limit, where they rule things out by a lot, that the limit that they actually get is like at the lower 95% bound of what they expected they would get, which might make you worry, maybe there's like a big downward fluctuation in the data right on top of the excess, and that's artificially strengthening their limit a bit. But I mean, even if they're just from the limit they expected, it would have been an order of magnitude below the excess. So, but yeah, I mean, but this, like the validity of this limit, that there are, I mean, it just seems to be true that the level of this, and this will come up again when we talk about, if we talk about the GCE, the background model for these analyses is not really good enough to fully explain the data down to the level of noise. So you can get systematic effects from your background model being bad. And those systematic effects vary as you change the energy range that you're fitting over. And so then the question becomes like, okay, how much do I trust my background model, and how worried am I about the systematic effects? And this is why this question that went back and forth was basically how many free parameters do we put in the background model, and what energy range do you fit over? Because the answer that you get for that can make the difference between whether you see a 3.5 kV signal or whether you exclude it in a given data set. So yeah, but yeah, so this is a case where, if you made me guess, I would guess it's probably not decaying sterile neutrinos. I would guess it's probably charge exchange. But I think that, we don't need to guess based on Occam's razor. Hopefully in the next few years, we'll actually get an observation with higher energy resolution, and that will tell us the answer. I guess I'll just say at the moment, since I kind of skipped this yesterday, and then I'll take this question, was I've been saying like the simple sterile neutrino explanation is excluded. So what do I mean by that? What I mean is that if you're looking at dark matter decay, the signal is, oh, there's a question up there. Sorry, I had missed that earlier. Why don't you ask your question, and then I'll say what I was going to.
Yeah, so my question was about the positron anomaly.
Sure.
I see that at like high energies, the uncertainties are relatively large.
Yep.
So I'm guessing they include systematics. And so I'm wondering, like, why is that?
So these uncertainties do, I think, include systematics, but the high energy uncertainties getting big is mostly a statistics effect. Like there just are not many positrons at the, once you're talking about like 800 GeV positrons, there aren't a lot of positrons. I don't know how many positrons go into this last error bar on AMS02. I remember that for Pamela, which was the preceding experiment, which only went up to somewhat lower energies, like at 200 GeV, their last data point had, I think, 10 positrons in it. So so if you have 10 positrons, just the statistical error is very roughly speaking y square root 10, which is 3. So on a log plot, like the relative error is big. So yeah, so I believe that is the main thing responsible for the increase in uncertainty at high energies here. It's just that there are not very many positrons. So square root of the number of positrons is a big number. So let me just go back and say, no, it's a good question. It's a really good question. So let me go back and say what I was going to say about the 3.5 kV line, which is that the decaying dark matter explanation is really easy to test, because in the sense that decaying dark matter signals only depend on the total amount of dark matter in a region, which is also what determines the gravitational effects of the dark matter in that region. So like that's the thing that we can map much more easily than like the dark matter density squared, whatever, averaged over a whole region. So this means that, you just say, like, if I've seen this signal in one galaxy cluster, you say, right, here's this other galaxy cluster that we think has just as much dark matter based on the speed of the particles in it. Let's look at that galaxy cluster. If we don't see a counterpart signal, then it's not dark matter. It's not dark matter decay. So, and that's the rationale behind all these cross tests of the 3.5 kV line. But I mean, I'm not saying, this is necessarily the right answer, but you could say, well, maybe it has something to do with exotic physics, but it's not as simple as just dark matter decay. And so there have been various proposals for that. Dark matter annihilation down at this level is a possibility, but I mean, it needs to be a very subthermal cross section. One example that was raised was the possibility of this idea, which is exciting dark matter. So this goes back to the inelastic dark matter models that we talked about a little bit before. If the dark matter has an excited state like 3.5 keV above the ground state, you can collisionally excite that state and then decay back down from it. So then in that case, it's still a decay process, but it's only a partial decay process. And the rate depends on the rate of collisional excitation, not the rate of decay. So that depends on the density squared of the dark matter distribution, because it's a two-body process. And it also depends on the velocity of the dark matter particles. So then that tends to give you like an enhancement in clusters where the dark matter is moving pretty fast, which is where the 3.5 keV line was first seen. And it gives you a suppression in much smaller systems like dwarf galaxies and the outskirts of the Milky Way, where the constraints are coming from. So, you know, that's like, this is one kind of knob you can turn if you want to get away from these limits. Another possibility that was studied a fair bit and some papers around the time this signal came out was you could have like conversion of an ALP into an X-ray photon, in an axion-like particle into an X-ray photon in the presence of magnetic fields, and that can give you a range of states. So this, I think the scenario in this case was like the dark matter itself decays to an axion-like particle, or to some other particle that can oscillate into a photon, and then that particle oscillates into the photon in the presence of a B field. So that means that your signal now depends on the strength of the ambient magnetic field. Clusters have big magnetic fields, much more so than dwarf galaxies. So this would again tend to enhance the signal in these large systems compared to the systems where most of the constraints are coming from. So, you know, there are other knobs that you can turn if the only problem is that you want to get away from constraints like this. But of course, as you make your model more complicated, it may also be less attractive. So, but these models generally, you know, these are things that with better energy resolution, we could try to distinguish what's going on. There was a question there.
I'm wondering if you can relate this 3 kV, 3.5 kV line with the kV excess on xenon T.
Yeah, good. So I know people have taught, I know people after the xenon one-time excess, I know people chatted about this a bit, like the sort of the simplest initial interpretation of the xenon one-ton was some kind of solar axion that was relativistic and whose like mass scale could be much lower, right? Like the KUV was an energy scale. I did not follow all the papers that came out after the xenon one-time excess, and so I don't actually know if people already wrote models which connected the two. Like I remember hearing people chat about it. I don't know if any of those chats turned into papers. Do you happen to know that?
Connections with the 511 kV line?
No, they want to connect to the xenon one-time excess and the 3.5 kV. Yeah. But yeah, we can have a look through the archive and see what people wrote and see if anyone drew a connection. There's not, but yeah, I mean, I guess there's the sort of the zeroth order simple models for the two of the sterile neutrino decaying versus like accelerated versus like relativistic solar axions don't seem to have that much in common with each other. But yeah, I mean, there may be a model that you can come up with that has some connection, but I don't remember seeing any, but again, I definitely did not read all the model building papers that came out after xenon one-time.
I think there are some papers that can recast the limits on the sign of theta or neutrinos into the action to photon coupling.
So in what sense?
I have to go to that, but I think this stuff can be recasted for actions.
So in the sense that like, sorry, I'm just trying to understand, in the sense that like X-ray constraints on the constraints on the sterile neutrino, can be recast into limits on the axion photon oscillation. I mean, that makes sense, I think, given that, yeah, like in a strong magnetic field, you could have relativistic axion-like particles converting into, so I guess, I mean, you could look at like these classes of models where you get the 3.5 kV line by, you know, you make an axion-like part, you make like dark matter decays, you make a relativistic axion-like particle, that axion-like particle converts into a photon in a magnetic field. You could try to ask, okay, if there was something like that in the spectrum and it was being emitted in the sun or by some other process, you know, could that be related xenon excess. But in both of those cases, I think like the mass of the axion has nothing to do with the energy of the signal. You see, like the energy of the signal you see is so yeah. I guess you could try to ask like, is the mixing angle that you need consistent? You could ask that question, but I don't think you can ask is the mass consistent, because I think in both cases there's a wide range of masses that would do it, because you're always dealing with relativistic particles. It's a good question. One.
So I don't think I appreciate why the sterile neutrino is the simplest. I mean, if I want something like a really charged particle, dark photon, something like that, does it just require too high of a charge that it's already ruled out?
So you want to have the Milli charge thing decay?
Yeah.
So what's it decaying into? Where is the charge going?
I mean, I could have some kind of dark photon that gives me some kind of what's wrong with that? Maybe.
So
maybe
if I've got a particle that carries a conserved charge, unless it can decay to something else that carries the same conserved charge, it would usually be stable, right? I mean, so we could think about like annihilation of Milli charged particles, like, but then so I could think about a case where like I annihilate Milli charged particles and like 3.5 keV Milli charged particles and make photons or whatever. But then I think if you have so if I have at this mass range, like if you're thinking about sort of 3.5 keV to 7 keV particles, then if they were in thermal contact with the standard model, then warm dark matter constraints are an issue, and so are Big Bang nucleosynthesis constraints. So usually you think about dark matter down here that is, like from freezing, or otherwise like not in thermal contact with the standard model. Again, decays are not a problem for that, because decays happen in the late universe and are very, very subdominant in the early universe. So decays are not an issue here. But if you want an appreciable annihilation signal today, usually that means there was a much bigger annihilation signal in the early universe, which may have been able to. But yeah, so I think people, so you could think about like, yeah, okay, what if I have like a P wave suppressed annihilation? I think for like scalar Milli charged dark matter, you can get like a P wave annihilation signal. So you could ask the question about like, okay, if I have some like non-thermally produced scalar, so my guess is it would be hard, so you could ask like, okay, suppose so if you want it to be thermally produced, you're going to run into warm dark matter and BBN limits for dark matter that's this light. If you want it to be non-thermally produced, but still have an annihilation cross-section large enough to see the signal, you may be in tension there. Like if you extrapolate this annihilation cross-section back to the early universe, it may have been large enough to put the two sectors in thermal contact, which means that you will hit the warm dark matter bounds again. But yeah, I think that there were some studies about trying to do this with some kind of annihilation of light dark matter. It's just that, yeah, you just have to be very careful that all that annihilation in the early universe is not gonna mess with the cosmology or couple your dark matter too tightly to the standard model and thus make it warm or count as a relativistic degree of freedom during Big Bang nucleosynthesis, on which there are pretty strong constraints. So the reason why I say sterile neutrino is the simplest in some ways is that the signals in different clusters look naively consistent with the decay interpretation, in the sense that, like regions where there's more dark matter seem to have more signal. So again, you look at these comparison plots this is under the assumption that what you're looking at is a decay, so that the signal just scales like with, some rate times the density of dark matter in the system. And you can see that under this assumption, they're broadly consistent with each other. That doesn't mean that you can't make another possibility work, but the sort of the naive scaling makes it look like, yeah, okay, decay could probably work here. And then if you say that decay is probably going to work, the reason why I say the sterile neutrino model is the simplest is I guess that this is a theory bias. Like, it's a model that's been around for a long time, that's been studied in a lot of depth, that we understand we think we understand what the constraints on that model are from cosmology, that it's not produced through freeze out, it's produced by this kind of resonant conversion, and 7 keV is probably like right around the bounds of the warm dark matter limits for this, but maybe not completely ruled out. So it's a well-studied model. The X-ray photon line from this model has been predicted as a signal since like 2000. So from the perspective of the people who've been working on the signal for 20 years, it was like, oh, that's the signal that we predicted back in 2000, like that, basically dead on. So that's the sense in which it's maybe like the simplest model. But yeah, there is some bias here. Well, I mean, maybe there's an equally simple model and it just didn't get as much attention in the literature 20 years ago. But
So did we meet the rates and the y-axis is really good? The one in the middle where we would have the 7 kV serial, what's the number?
so sorry, in this plot, you want to look at the y-axis?
Yeah. So that's the mixing angle between the serial
Yeah.
and the.
Yeah.
Okay, so this, I think this would be something that the system project could see.
Maybe. Yeah. Okay. Yeah. I think. Okay. Yeah. That's quite possible. I saw a talk in the context of the snowmass process last year, which was saying that yeah, one of the sterile neutrino search experiments might be able to go after this.
The mass is definitely in the region. That
Okay. Good to know. The experiment is Tristan, you said?
Yeah, it's an extension of the Katrin experiment.
Okay.
They put in this Tristan detector up to the normal Katrin line and just could see the sterile neutrinos in the experiment space.
What's the time scale?
I think they did some measurements at the twice experiment already, but I don't know in this region.
Okay.
Katrin will run for the next 3-4 years, and then they will put in the Tristan detector.
Okay, cool. Yeah, that definitely looks like something following up on to see if they can prove this range. Good.
Good follow-up there. So we're looking at.
Why didn't you hold on to the mic for a moment? Oh no, okay, I guess we can trade it back and forth. Yeah.
I mean, we were looking at the mixing with, I guess, one of the neutrinos, right? I don't know what they did here.
Yeah, I don't remember how they generally parameterize this. Is probably the mixing with the. I don't remember what they assume for the mixing with the different
Sure,
neutrino
but
species.
I guess my question is, we could also set constraints on the mixing with the sterile and the tau, or the sterile and the.
Yeah, so for the purposes of this signal, I don't think it really matters because the only thing you're seeing is the photon. So, right, like I mean, so the process that you're imagining is right. Sorry, now I'm just trying to remember what the diagram looks like. But I mean, the process that you're imagining is that a sterile neutrino decays into a neutrino and a photon. And that there must be like a W loop. There must be like a W loop in here, and the charge W is allowing the gamma to go off. So so because of that, I am not sure. Like I don't think we care about what the flavor of the neutrino is.
Well, I guess
getting hit. So
I don't know, if I had appreciable mixings with all of the active neutrinos, then I could boost my signal by 3 times or something, right?
but we don't. Right. So I mean, I guess. So like, yes, I think that's true, but I don't think we know what the. I mean. It's like, so you could boost your signal 3 times relative to one that only mixed with like the electron neutrino, maybe, but. I mean, we don't like. We don't know what the underlying mixing should be to any of these, right? So I mean, I'm not sure you can tell the difference between I have a mixing of X to only one neutrino species, and I have a mixing of X over 3 to each of 3 different neutrino species in the context of this.
I guess I've just imagined that this plot should really have more axes for the mixing between sterile and different.
But I think it's degenerate, right? Like, I mean, I think from what we can see at the moment, like, I mean, all you can see is like, what is the probability that this decays and emits a photon and something else? And like the X is unconstrained, provided that it's close to massless.
Okay.
So I think we only have one piece of information. Yeah. Okay. Did you want to say something?
I think the mixing is with the mass aggregate of the not from the.
Yeah.
Then you have one parameter, and then that parameter can.
Governs the mixing for the other. Yeah, just depending on their masses. Yeah, that's probably right. But I mean, like, even if there were multiple parameters in the mixing matrix, like even if, we have like other sterile neutrinos in the matrix or something like that, I think from this particular observation, what you get is like one number. So whether that's like, a linear combination of some set of mixings.
But when I compare it to the model, I mean, I can't predict theta 2,4 and theta 3,4 from just one of my thetas, right? Okay.
So
Maybe I just answer.
yeah, thanks, you're right, thanks.
So this is a mixing angle into standard model neutrinos, and it's one linear combination, right? And then this linear combination has mixing angles into the mass state, so it's completely irrelevant to Tracy says. This is the right, you can reconstruct the theta 1,4, theta 2,4, theta 3,4, but it's a one parameter which is just telling you the mixing between this guy and the linear combination. Can I draw some diagrams once we get back to that?
Sure.
My question is about the anti-proton bump. So I don't know if anybody else has questions about this.
We can go back and forth. Let's talk about antiprotons. Yeah.
So I have no idea whether this would be possible, but I'm wondering, you said that would like dark matter in a reasonable mass range is potentially a good candidate for explaining this.
If it's real. Well, I mean, that's the thing about this bump. It's not actually super clear there is a statistically significant bump there, but yeah.
Yeah. Are there any collider searches that could put constraints on an interaction between WIMP-like dark matter and an antiproton?
So there are lots of potential ways to constrain 40 to 130 GeV WIMP-like dark matter. And there was actually a ton of model building for this in the context of the galactic center access, which prefers like a similar mass range and also wants to probably couple the dark matter to black hadronic states, to quarks. I guess, Caleb, do you want to comment on this? I can say a bit about the model building.
My question.
Okay, very good. Okay. So let me actually flip over to what I had about the GCE, because I think quite a lot of this probably applies pretty equally to the antiproton excess in terms of how you model build for this. So right. So if you think that what you might be looking at is a signal of like order 50 to 100 GeV annihilating in a way that makes quarks, which is a necessity if you're going to make antiprotons. Less so for the GCE, but I mean, it was a nice fit to the GCE, so there was a lot of interest in it. Then you have these questions of direct detection's really sensitive for 30 GeV. Like 30 GeV is like the absolute peak of the direct detection sensitivity for WIMPs. So why haven't we seen it yet? And also, what about bounds from collider searches? Like we have the Lecture6, it's fantastic at smashing particles together at much higher energies than 30 or 100 GeV. So are there bounds from this? So. And the zeroth order answer is there are various knobs that you can turn to make a big signal in indirect detection without getting a counterpart. So certainly lots of models are constrained, but there are classes of models that you can pick that are visible in indirect detection and will not yet be visible in colliders or direct detection. And some of them are really hard to see even in the future, and some of them are kind of around the corner. So there's the whole range. So this is like a slide that I've been using since around 2050 for this question. So, if you ask why haven't we seen it in direct detection? Well, so the annihilation could be going through some kind of resonance, and that resonance is not available in the scattering states. Like there's some other particle which is twice the mass of the dark matter, and that enhances. And so you go through that in the S channel, and that enhances the annihilation in a way that does not enhance the direct detection. The direct detection signal could be dominantly spin dependent or suppressed by some like Q² factor in the matrix element. Another possibility is you can have a situation where the annihilation is to like invisible mediators, which subsequently decay to the standard model. So in that case, the small parameter is usually the mixing between the mediator and the standard model. But for indirect detection, that mixing only matters for working out the decay lifetime of the mediators. So I'm going to draw on the board here. So your picture here is so in these models, I just So in these models, you have a situation like, we'll call this, like A prime. We call this the dark matter. So you have an annihilation like this. This is phosphate. These are on shell A primes. And then at some later time, the A prime decays into, say, an electron and a positron or some other standard model particles. So in this case, if this is your setup, then this, this epsilon, all it does in indirect detection is determines the decay lifetime for this step. So long as this decay lifetime is relatively short, like a second or less, then it won't mess with BBM. And from an astrophysical perspective, if the decay happens in a second, like it's instant. These signals from the galactic center take us. The galactic center is like 25,000 light years away. These signals take 25,000 years to get here. A second more or less is nothing, right? So in this case, so for direct detection, what determines the strength of your signal is like this coupling in the dark center. But for direct detection, you have a standard model nucleus over here. So for direct detection, the diagram looks like this. Okay. And so the epsilon shows up already in your cross section. And the same with colliders. Like if I'm trying to produce this A prime or produce the dark matter in a collider, then I'm going to have to go through this small epsilon. So if epsilon is small enough, you can have a situation where the direct detection cross section is pretty big because it depends only on the start stage of coupling, which can be quite large. But the indirect detection and collider searches are suppressed by the small epsilon. Now, at the same time, there are lots of constraints on this type of model. If the A prime is really light, you have a big Sommerfeld enhancement. But if both the chi and the A prime are relatively heavy, then these kinds of models can still be viable. So yeah, so like this sort of like decoupling of the coupling that determines direct detection in colliders from the coupling that determines indirect detection is one way to end up with a big hierarchy between the signals. So yeah, that's one of the knobs that you can play with. And so people at this time back around 2014 did this exercise of testing. I'm just going to play the slideshow here. Did this exercise of saying, okay, let's just write down a whole bunch of effective field theory operators that could couple the dark matter to the standard model of quarks. So this is the Dirac fermion dark matter for scalar dark matter, just studying the couplings to hadronic states, and then ask how many of them we can already kill. And it's like, these ones you can all kill because we would have seen it in direct detection, but like all the others, we wouldn't have seen it in direct detection because the signal is like spin dependent or suppressed by the momentum transfer, which is a small number. Okay. These ones you can kill because they're like P-wave suppressed. And so it's hard to get an indirect detection signal big enough to fit. So this was for the galactic center excess, but again, it's a similar parameter space to the anti-proton excess. And these ones, and then these three are killed, there are others that the LHC can test, but these three are not ruled out by direct detection or indirect detection, but are ruled out by the LHC. And so then that leaves you with a relatively small set of operators to look at in the effective field theory context. Now, effective field theory isn't always good. Like if you have light mediators in the problems that you can't integrate out, then you can't necessarily just use these effective field theory results. So then this paper looked at a whole range of simplified models with just sort of scanning over what is the dark matter, what is the mediator, and they summarized you can see the summary of the reach on the right-hand side, which is basically does direct detection of the LHC have near future reach, and you can see that in both cases the answers range from, well, for the LHC, the answers range from maybe to yes. From direct detection, the answers range from no to yes. Range from never through maybe to yes. So
from never from the.
I think that means below the neutrino floor. Like well below the neutrino floor. I think that is what never means in that case. Yeah. So in that case, the situation is it's a spin-dependent scattering that is also suppressed by Q squared, where Q is the momentum transfer. So that's a pretty small signal. Yeah. So anyway, so that and you can write down some specific models, which at least in 2014 or 2015 were not excluded by anything. There have been, there are real, so this was one idea where there's a pseudo-scalar mediator which I think suppresses the direct detection signal. There are variants of this where it's like a pseudoscalar that mixes with, where you add a pseudoscalar Higgs into the standard model. So it's this 2 Higgs doublet model. And then that pseudoscalar Higgs mixes with the pseudoscalar mediator, and the pseudoscalar mediator couples to the dark matter. So that was worked out here. And there are implementations of this general idea within supersymmetric frameworks as well that people have worked out in the literature. And then you have like the model that I was talking about here, where the dark matter goes to a mediator, and then the mediator decays in the standard model stuff. And there are various implementations of this. These references are all from like 2014, because that was when there was a big surge of model building for the galactic center access in the community. But there's a later, like there's an NMSS, there's another NMSSM paper from like just a couple of years ago, after the dark matter interpretation game for the galactic center access gained a bit more credits. So it's a really good question. Like for any of these, so I hope you know what this gets across is for these signals, we often do have like good cross checks, but in going between indirect detection and other searches, there's a fair bit of model dependence, which on one hand like is really cool, because it means that, you know, if you did decide that this was a confirmed dark matter signal, so you know, suppose you saw counterpart signals in dwarf galaxies, which were much cleaner and low background, and you convinced yourself that it really was likely a dark matter signal, then the fact that we haven't seen it yet in direct detection or collider searches like tells us a ton. I mean, it excludes a huge range of possible models and sort of narrows you down to a few, to a relatively small number of possibilities. But of course it would be better if we saw a counterpart in direct detection of collider searches. That would be convincing. But it's hard to completely exclude the possibility that an indirect detection signal is dark matter solely from direct and collider searches. And similarly, like if we saw a signal in direct or collider searches, it would be hard, like only not from seeing an indirect detection signal to rule out that it was dark matter, because if it was p-wave suppressed or asymmetric, then there can be plenty of sensible models where you would just expect to see no signal in indirect detection. Is that?
Yes.
Yeah, great. You had your question lined up.
Yeah, so this is relevant to the anti-proton excess, but also in general for like statistical uncertainty excesses. So say I have a model I want to test. How much does it affect my ability to say use this data to constrain a model? Or does it even make sense to like both do a fit to the excess and constrain?
Yeah, good. So that's like, so that, you know, that's, so this is a great question. So this is like, you know, this search here, where we see that there's a constraint on, you know, like that there's a constraint on annihilation into antiprotons at higher masses, but then this constraint line takes this big upward jump right around the spot where there's an excess, so the constraint gets much weaker there. And so that's one statistical analysis, and then the alternative analysis is you say, okay, then what is the actual best fit, and you know what are the contours around that actual best fit value. So yeah, usually so in all of these analyses, what you're typically doing is you're saying, all right, I have a model, I have some data points. Let us try to, so in a frequentist analysis, you say, let us work out the likelihood or some approximation to the likelihood, which is the probability of getting the observed data given your model. It is not the probability that the model is true given your data. To do that, to try to get at that, you need to do Bayesian statistics, which means you need to put in a prior, so you know that your particular model parameters are actually the case. But yeah, so like this was a frequentist analysis. I think Kui et al. Was a Bayesian analysis, so you can do it both ways. But it's kind of likelihood analysis. What you're going to do is just say, all right, so then as a function of the parameters of my model, what is the maximum likelihood, and how much do I need to increase my cross section before my likelihood has dropped a certain amount from my maximum likelihood, and that can correspond to like a 95% confidence or a 68% confidence or a 99% confidence of the usual values. Now, often, you know, the experiments won't give you the full likelihood bin by bin, and what people typically assume then is just like some kind of Gaussian likelihood, and just tell you that the error bars tell you about sort of the one. So then you're essentially doing like a least squares approximation to the likelihood. And so it's the same thing. So it's basically the same procedure when you're asking about, it's basically the same procedure when you're asking about, you know, have I detected something? And what is the range of cross sections which give me a good fit to what I've detected? The difference is just that if you've detected something, what it means is that the maximum of the likelihood is statistically different from zero. So because you always want to measure like the difference from the maximum, you want to measure the differences from the maximum, the likelihood. If the maximum, the likelihood is well away from zero, then the upper limit is also going to get a lot weaker, because now you need to look for, okay, where has the likelihood dropped off this much from the maximum, but the maximum was occurring in a value of the cross section that was already pretty large. So you're not going to get a value of the likelihood that is significantly smaller until an even larger value of the cross section. So the effect will be both to weaken the limit, and so you can either just ask, okay, how much does my limit weaken, or you can say, okay, and where is my actual best fit point, and is it statistically different from zero? So yeah, like they're very closely related analyses, and you're basically computing the same thing, which is the likelihood as a function of cross section. You're then just reading off different things. But yes, so you can see in this case, if you had sort of naively extrapolated this bound down here, it would be, so like the fact that there's an excess here, locally for sigma excess is weakening the bound by about an order of magnitude. So this actually comes up, so say in the context of the positron excess. So this also depends how you want to model your background. So there's one way to treat constraints on dark matter annihilation from the positron excess, which says the background model that we should use, on which we superimpose our signal model to compare to the data, should be like our standard secondary production model for positrons, which would look like this, okay? So if you do that, you're not going to get any useful constraints on dark matter for like higher mass dark matter, because there's this huge signal here. So like, even if your dark matter doesn't fit that signal at all, so long as it's below the signal, you might say then, okay, it's not constrained. The other thing to do, which is what people usually actually do for doing constraints, is to say, okay, let us take the presumption that this bump is not coming from dark matter, but that it is coming from some background. So then let's put in a model for that background, which could be a physical model, or could be just say, okay, I'm just going to like have some smooth function that approximately fits this excess. And then we're going to try to exclude like structure on top of that smooth function. And so in that case, you're tacitly assuming that there's pulsars or something else that is giving you a smooth signal that looks like this. And what you're excluding is little bumps on top of that smooth function. That will give you much stronger limits, but you've got to be pretty careful, because it's possible that your like smooth background model is just absorbing a lot of your signal. So so usually what you want to do in that case is give your smooth background model like a decent amount of freedom, so that it can it can adjust itself to accommodate for a reasonable dark matter signal. And then the question just becomes, okay, like, how do I pick how many degrees of freedom I'm going to give my background model if I don't have a physical understanding of where that signal is coming from? And that can be tricky. So then people will often show something like a conservative limit, which is if you just assume that the background is the conventional background and is way down here, and any dark matter signal smaller than this bump is okay. And they'll also show, like a less conservative limit where you assume some kind of simple parameterization for a smooth background here, or physically motivated parameterization for a smooth background through here, and then constrain bumps on top of it. But that second approach also tends to have the feature that there will be kinds of dark matter models that you just really can't constrain at all. Like, suppose you have a dark matter model that just sort of has like a smooth bump that has more or less the same, that predicts like a smooth bump that has more or less the same shape as this, but like a factor of 10 smaller. Then like, there's no reasonable background model that's going to let you exclude that, because you're not, I mean, if you don't physically know where the background comes from, that, like, there's no way that you should be able to say, okay, well, something that looks just like this but is 10% smaller is excluded. But if your model predicts, like, if suppose your model is dark matter annihilates straight to electrons and positrons, so then that gives you a delta function injection, which means after propagation, you have like a hard spectrum and then a very sharp cutoff. Then, you might reasonably say, well, so we're going to look for evidence of a very sharp cutoff in the spectrum, and we don't see it anywhere. So in order to compensate that very sharp cutoff, my background model would need to have like a sharp upturn at exactly the same point. You can say, okay, that's not very physical. There's no way that the pulsar spectrum should suddenly go like this. And so then you may be able to put a reasonably strong constraint on a model that has a sharp cutoff like that. So that's why the limits on E plus E minus annihilation from the positrons tend to be like much better than the limits on annihilation to muons or annihilation to taus. It's not so much the power, I mean, part of it is the power into electrons and positrons, but a fair bit of it is just that the spectral shape is a lot more distinguishable from background in the case of E plus E minus. Does that help?
Okay. So one thing I've been thinking about, and I saw at least one paper on it, and I guess I'm curious about your opinion.
Yeah.
So something like studying these really charged particles in the form of like synchrotron radiation or some kind of acceleration through astrophysical means.
Yeah.
Can you get competitive bounds with something like this?
It's a good question. So, okay, so we're interested in the case where we've got milli charged dark matter, and as it passes through the radiation field of the galaxy, it radiates synchrotron.
And I've that, and I've seen something, I don't know how it works, so something they get accelerated by these supernova,
Yeah.
something like this. Yeah.
So the supernova acceleration I've seen mostly in the context of the question of could milli-charged particles get accelerated by supernovae, kicked out of the galaxy, and then be unable to get back into the galaxy because of the galactic magnetic field. And the reason why people are interested in this question is that if this happens, it means it would be very hard to see milli-charged particles in direct detection experiments, which might otherwise have a lot of sensitivity. Like if they all get evacuated from the galaxy, you're probably not going to see them making trouble in xenon or whatever. So there were some earlier papers that suggested, based on estimates, that they should be almost completely evacuated. So you would have basically 0 milli-charged particles in the neighborhood of the Earth. But then there have been some more recent studies.
But that would pretty sensitively depend on how many charged they are, right?
Maybe not, actually. Like they just need to get accelerated. They just need to get kicked out enough. I guess they just need to have enough milli-charged. Yeah. I'm not actually sure of the answer to that question. But so this paper by Dunsky et al. From 2019 restudied this question. They concluded that actually, while the milli-charged DM does get kicked out by supernovae, it doesn't get kept out. Like it can diffuse pretty efficiently back into the Milky Way. So that's an example of a study I've seen about milli-charged DM in supernovae. So the synchrotron question is interesting. I mean, I guess the thing that so the context in which I'm used to thinking about synchrotron is relativistic electrons. And I know how the behavior scales in that case, which is that it goes like the energy of the electron squared. But here you'd be talking about very non-relativistic particles.
Right. And part of the thing I was thinking about is if you could find some place where dark matter is being produced very energetically, and you have something.
Okay, I see. So you want relativistic dark matter cosmic rays producing synchrotron radiation. Oh, that's
about these slow movers, and I mean maybe you could get some kind of distinct or unique synchrotron radiation even from something proven very slow.
Yeah, so I mean, okay, I'm going to make stuff up now. Okay, other people should feel free to chime in and speak up. So just from what I know about the scaling of synchrotron radiation energy, so even if I think about pretty relativistic electrons, like 20 or 30 GeV electrons, the synchrotron so the magnetic field of the galaxy as a whole is only a few microgauss. And if you plug in those numbers and ask what energy that synchrotron radiation is from 20 GeV electrons, you find that it's in the microwave. So, and the typical energy of the synchrotron, I think, scales like the energy of the electron squared. I think might just be the energy of the electron. People should correct me if I'm misremembering. It's quite big. So then I would think that if you're talking about non-relativistic particles, my naive expectation would be that the energy would be much lower. So you're probably deep in the radio if you get a signal at all. That might be hard to see. But maybe it's worth looking at, given that these 21 centimeter experiments are all, going to try to do searches deep in the radio.
Why do you say it'd be hard to see?
Just because it's very low energy and there are huge backgrounds. So I would guess the flux is small, the energy of the photons is small, and there are lots of ways to make radio photons in our galaxy. So my guess is it would be hard, but it's maybe worth doing the estimate. The other thing that Yeah, so when you think about like, you know, dark cosmic rays and what they could do, so that's interesting. I mean, so you're going to be penalized by, so like your rate is I need to think about what the effective epsilon does. So I mean that'll reduce the cross section. Like in, you know, normally we're thinking about like the electron proton interaction cross section, so as the Thomson cross section. Your cross section is going to be suppressed by a like epsilon. You know, if the Milli charge is epsilon, your cross section is, I guess, going to be suppressed by probably an epsilon squared factor. So so I guess my guess is it's going to be pretty hard to see this against the background of synchrotron from the ordinary electrons, but it is, I mean, there is a different mass scale. Yeah, so I guess the question is like, does the different mass scale give you any interesting difference in the spectral behavior? Because like the signal is going to be much smaller, but could you get like any kind of different spectral feature? But the problem is that like if the emission is basically ends up just looking like a power law, and it looks like a power law that's similar to the electrons in the galaxy because they're being accelerated by the same supernova, then it seems like it would probably just be something that had like a fairly similar spectrum, but much from the relativistic particles. That you might guess it would just be like a fairly similar spectrum, but with much lower amplitude, and then it's hard for me to see how you would see it. But so maybe you need to see like the turnover to non-relativistic behavior in order to distinguish them. Again, so short answer is I don't know. I remember there was some papers maybe by like Lorenzo Ubaldi a few years ago on looking for dark matter accelerated in AGN jets. And so this was not for Milli charged dark matter. This was for like dark matter colliding with the gas in AGN jets and producing signals from that. So yeah, I mean, maybe it's worth taking a look at that, seeing if there's anything that might be useful there.
So for standard model radio background, is this just non-relativistic electrons? Synchrotron radiation? Or would it make that
I think
combination?
even, well, so like I said, like 20 GeV electrons make microwaves, and I think, and Marco, you said it goes like energy squared, the energy of the outgoing synchrotron. So yeah, so if I go down even to like 20 MeV, that's still a relativistic electron. That means that I've dropped 6 orders of magnitude in energy. So like that will be very firmly into the radio band. So I mean, I think, like, I mean, there's a synchrotron background just from like relativistic electrons, but not, you know, tens of GeV electrons producing synchrotron. There'll also be thermal emission from the galaxy down at those frequencies. So like the temperature, the temperature of the CMB is 2 × 10⁻⁴ eV. The gas is somewhat hotter than that. So I mean, if you think about like backgrounds for the CMB, which is in the microwave, so there are backgrounds from thermal dust, there are backgrounds from spinning dust, and there are backgrounds from synchrotron radiation. But I think like synchrotron is the relatively soft component, so it's more important at the lower energies. So you might look at like the Arcade experiment, which was an all-sky radio experiment, which actually has an excess in it. So, you know, if there's an excess or anomaly that you want to explain, I mean, you could look at the Arcade result and at the Edges result. I think they're probably the most sensitive observations, at least of the whole sky, that we have down at that end. There may be more sensitive targeted observations on supernovae. So yeah, that's my. I don't know, Michael, if you have anything you want to add. That's my sort of random. But I mean, yeah, it's an interesting idea. It's something that you could something to look into. But I do worry though that, you know, if you probably need there to be a distinct spectral feature to be able to tell, and the only thing I can see that would obviously give rise to that spectral feature would be something to do with dark matter mass. But then that's probably corresponding to a pretty low energy. But yeah, like, I mean, you know, figure out what energy it would be given the. I mean, you might also be able to take advantage of regions with higher B fields, like around, you know, around, you know, pulsar magnetospheres and
Is
stuff.
there kind of software to study synchrotron radiation?
I can point you. So there's a pretty simple formula for like the critical frequency of the synchrotron radiation. I can point you to a reference. There's this physics reports paper from like the 1980s that I use as my standard reference for synchrotron and ICS. I can give that to you later. But yeah, there's a fairly simple formula for what the critical frequency is. Okay, great question up there.
So I have a remark on the galaxy center access, not for your question.
Yeah.
Yesterday you show a plot of the morphology of the galaxy center access. I think it's with the next slide.
Yes. It's not plot.
Yeah, the one on the right. And this plot indicates great morphology for the galaxy center access, but I think this plot is a bit outdated. And there have been recent studies. One paper by Aug6 in 2019 indicating that the morphology of the galactic center access was more of a and the morphology is important because it can indicate different explanations. So the circle morphology indicates it's in favor of the dark matter activity for the
yeah, this is one of the slides that I skipped last night for lack of time. So this is exactly what I was saying here. So yeah, so right, so yeah, so let's just go through my GCE slides and I can say that. So the arguments against so the arguments against the GC, so the argument in favor of the arguments in favor of the GC being dark matter were that it's relatively easy to get the energy spectrum right, that the cross-section unity is pretty much bang on with the Morellic cross-section, and that the early studies of the morphology found that it was pretty spherically symmetric, which is what you might expect from the interior of the DM Hiller. However, as you said, there have been more recent studies which instead find that the spatial morphology is better described as sort of like a boxy bulge-like extended emission and a central nuclear bulge component. Now, so this is really interesting. And there are basically two kinds of studies in this direction. So one is the stuff by Oscar. So one of the studies by Oscar Mikies et al. And the other set of studies is by the group in Amsterdam with Christoph Weniger and Francesca Colore and the students, which used a different approach to modeling the backgrounds. And these both independently found some preference for a bulge-like morphology. So, however, the answer that you get for the morphology is sensitive to how you model the backgrounds, which is why there was a difference from the early studies to these later studies. There's another reason, and you know, and it's not just like a function of time. There was this other recent study by DiMauro et al., which used a different background modeling and you know, tested the bulge against the spherical morphology and found that the spherical morphology was a benefit, which we also did in the early studies. Like we tested bulge-like morphologies, we found the spherical morphology was a benefit. But the reason for this is it's a function of how you model the backgrounds. So, okay, so the backgrounds for this case are when, as we've talked about earlier, when protons hit the gas, they provide a spray, they produce a spray of particles, which can produce gamma rays as well as other charged particles. And so there's a large fraction of emission, like 80 to 90% in this energy range, in this region of the sky, comes from protons hitting the gas. So you'll get, so understanding, and this is really hard to predict from first principles because so we basically understand that it's proton-proton collisions and electron-proton collisions from electrons interacting with the starlight. But in order to get a fully accurate prediction of what all this emission would be, what you would need is like the full 3D map of where all the gas is in the galaxy, compared with the 16 phase space distributions of where all the cosmic rays are in the galaxy, compared with the 3D radiation field everywhere in the galaxy. And we just don't have that information because we can only do observations from one point, which is about. So like that, I mean, it's not, when I say like the background models are not great, it's not because the people building the background models are stupid or anything, it's because there's a limited data set to try to unfold this detailed information. So, right, so the older way of building background models is to use maps of the gas, which are based on like an observation. So you can build these maps in different ways, but the basic ingredients are you can observe atomic emission and absorption lines from different species of the gas. And you can use infrared emission from the dust, which is a pretty good tracer of the gas, to try to map out where the gas is. And you can use Doppler shifting of those lines to try to estimate what velocity the gas is going relative to us. And for most of the galaxy, that also allows you to get a rough estimate of how far away it is. So this gives you, the problem towards the galactic center is that because we're rotating around the galactic disk, objects at the galactic center have very little line of sight velocity relative to us. Like our velocity relative to them is largely tangential, which means that the look at the Doppler shift of the lines to try to figure out how far away it is doesn't really work, because everywhere along our line of sight to the galactic center doesn't have a lot of line of sight velocity relative to us. So the inner galaxy region is kind of uniquely bad in being able to figure out where exactly along the line of sight the gas is. So, but still, the traditional way to do it is to try to, build up this estimated 3D model of where the gas is, use a program like Galprop or Dragon to estimate the distribution of cosmic rays throughout the galaxy, and then multiply these results together to try to get a prediction for the gamma ray emission associated with the gas, and then divide this emission into galactocentric rings, and then float the galactocentric rings independently and try to fit them to the data. It's kind of the traditional way of doing this. This gives models which typically explain the gamma ray emission over most of the galaxy to the percent level. Given the number of photons that Fermi has, this is nowhere near being a formally good fit. Okay, so you can explain 99% of the emission. That doesn't mean you have a good fit to the data, which means that there can be systematics associated with that mismodeling, which can affect things like the galactic center excess. So using these using this sort of Galprop plus gas maps based approach, you find that the galactic center excess looks pretty spherical. What McKeer et al. Did was said, we don't necessarily believe the distribution of the gas coming out of these maps, especially close to the galactic center on a small scale. So we're going to use hydrodynamic simulations of the gas distribution to try to modify the gas maps. This gives maps which are a somewhat better, just like they are a formally better fit to the data, but they are still not a good fit. When you use those maps instead, when you use those maps instead, and also their prescriptions for region of interest and point sources, you get bulge-like emission. I would say, so like this is not formal. This is very preliminary. This has been verified, but this is not being like verified by other people. So like take with a big grain of salt. But like, I mean, I and other people have tried to confirm this bulge result where we use some of their analysis, but not other parts, like using their background models, but a different prescription for point sources, or using their background models, but a different region of interest. And we don't find that the bulge preference is always there. So like, I mean, it depends on these things. Now, that's it. Like, it could well be true that their background models are absolutely, well, I mean, they're not perfectly correct, they're not good fits, but it could very well be true that by using these hydrodynamic simulations, they have captured a kind of systematic error in the earlier analyses that was making something bulge-like look like more spherical symmetry. That's a totally viable possibility for what could be going on. But it's also possible that this is a knob you can turn. When you turn this knob to make these models slightly better, the preference went from spherical morphology to bulge-like morphology, but there might be other improvements to the background models that you could make which would move the preference around again, because we're still not at the stage where these models are good fits to the data. The argument, so a possible argument against that happening is that the Bartels et al. Paper, they did an alternative way of modeling the backgrounds, basically where they gave the background model, thousands of extra degrees of freedom to allow the gas maps to adjust itself to explain the gamma ray distribution on a pixel by pixel basis. And so they did a model that is actually formally a good fit to the data, but at the cost of needing thousands of extra degrees of freedom. And they found that, and they also found like a more bulge-like morphology that is less spherically symmetric. So like that's pretty interesting. Like I think so to me again, so this is now my personal opinion. What that says to me is that at the level of knowledge that we have about the gas distribution at present, it is totally possible to have a well-fitting model which is consistent with all the data that we have on the external data that we have on the gas distribution, and it has a bulge-like galactic center excess. Their work tells me that that is a possibility, which in turn tells me that like there is no modification to how we model the gas within our current uncertainties that will allow us to say it is definitely like a spherical morphology, because like we have an existence proof of a good fitting model with a reasonable background that is consistent with what we currently know and bulge like galactic center excess. So like that has to be a viable possibility. But to me, it is not quite the same to say this is consistent within the uncertainties and this is the only possibility within the uncertainties. So for that reason, I'm not completely convinced that we have proved the galactic center excess morphology is bulge-like. I agree it is totally consistent with what we know at the moment, if the excess morphology is bulge-like. And if I was convinced that like our background modeling has converged to the point that any reasonable modification of the background model will still have it being bulge-like, then I agree. That would be really, really good evidence against the dark matter interpretation. For me at the moment, it's one piece of evidence against the dark matter interpretation, because if it looks like the bulge, that's like a strong indication that will be of some kind of stellar origin. But I would like there to be a second piece of evidence. You know, I would like, to be really confident, I would ideally like there to be two lines of argument that go in the same direction. And a couple of years ago, I thought that we had those two lines of argument, which was why I was pretty confident that it was pulsars. But now I'm less confident in the second line of argument. But yeah, like, I mean, I know if you want to comment on this, but like, yeah, you're absolutely correct that there's some, that this morphology issue is, but potentially a really good handle on the behavior of the excess and the, yeah, and that at the moment, this together with the energy spectrum are the two reasons that I think the pulsar interpretation is probably preferred. Like if I've said this to people over dinner, but you know, if you made me put money on it, I would, you know, if you said you have to pick, you have to pick one explanation, I would probably bet on this being some kind of pulsar population. But I don't think it's pulsars at 99% confidence, or like even like 95% confidence, but because of these ongoing questions about the background with regard to the morphology. Does that make sense? Yeah. But I mean, I know other people who are more convinced, like by the morphology argument, who are like, I feel this is really strong evidence. Yeah, question.
So I have a question related to the dark matter. Yes, so I have a question related to dark matter annihilation and the CMB.
Yeah. Yeah, no, that's good. That's fine.
So yeah, you were mentioning these back reaction effects.
Yeah.
When discussing the dark matter annihilation. So the fact that the energy injection is very high could modify the propagation of the electromagnetic cascade itself. So, I mean, to check that, what one should do in general is to solve this propagation equation simultaneously with the recombination equations from breakfast.
Yep.
So that is being done?
Yes, that's what the dark history. So right, so this was done by me and my students in Hongwan Liu, who is now a postdoc at NYU and Princeton, and Greg Ridgway were the ones who did most of the work of actually writing the code. But yeah, my students and I did this back in 2019. So it's a public code package called Dark History. You can download it from GitHub. It's currently, I will warn you that if you download all the accompanying data files from GitHub, it will take up a decent amount of space in your hard drive, like multiple gigabytes. So we are currently working on improvements to Dark History, and Wenza is one of the people leading these improvements to Dark History, which do two things. One of the sets of improvements is to improve the treatment of low energy particles, which is currently pretty approximate. And the other is to replace the giant interpolation tables, which we currently make you download, with a neural network, which can just emulate the results of those interpolation tables, which will hopefully mean that you are downloading like less than a megabyte instead of 10 gigabytes. So yeah. So, but yeah, that was, this. So it turns out that those back reaction effects are basically unimportant for the CMB constraints, because this is happening because at the redshifts where the CMB constraints are most important, the modification to the ionization history that you can make without falling afoul of Planck is reasonably small. So it turns out to like just be a really good approximation to ignore back reaction for a redshift higher than about 100. And the CMB constraint for annihilation peaks at like redshift 600. So it's for the CMB, you don't need, like, having done the calculation carefully, you don't need to worry about back reaction. But where back reaction can become important, and I think I actually have a figure here which demonstrates it. Maybe. Okay, maybe I don't. Yeah, okay. I may not have it in here, but I can show it to you later. Where it may become, where that, sorry, yeah, okay, actually, yes, it is the time. So where it does become important is at late times, where, so like in the lead up to reionization and through reionization, where you can heat up the unit. Well, okay, this may be less true after the Lyman alpha constraints that Wenza and colleagues worked out, but around reionization, you can dump a lot more because the universe is getting heated up by the stars and stuff. You can actually dump quite a lot of energy into the standard model without being excluded because there are other sources. And then at that point, the back reaction effects can become important. Like we found that it can change the taking this into account, and for temperature, it's actually a positive feedback effect. Like as you dump in more power, you ionize the gas more, and that makes the heating more efficient, which, you know, and so like the back reaction actually enhances the signal. And we found that in some cases it could enhance the signal by like 1 order of magnitude.
So this means that for 21 centimeter survey, this should be taken into account. This
Yes.
Okay.
Well, so this is interesting actually. For Lyman alpha surveys, you need to take it into account. For 21 centimeter, you should take it into account, but if the 21 centimeter surveys have the sensitivity that we think we might have, then they will actually rule out the region of parameter space where back reaction is important. Like, and may rule it out even if you ignore the back reaction. So then it'll be more like the CMB, where back reaction can be important, but if you don't see a signal, then you know you're in the regime where back reaction is not important. And so then it may be self-consistent to ignore.
Okay, so we're getting very close to that. Great. So I think we should thank Tracy very much for her lectures.
I have not really, sorry, I made